Hello and welcome to Loomis Laboratory. In this video, I'll be summarizing what I learned in week 3 of my first semester of my third year program. Check the description for more information. Complicated algorithms uniformly generate numbers between 0 and 1. These can be augmented to produce numbers of any distribution. A simple technique is to pick random coordinates uniformly within a box drawn around the distribution, keeping the choice if it falls under the curve. We can also use the inverse of the cumulative density function in order to assign numbers between 0 and 1 to a corresponding number on any distribution. If not available analytically, we may computationally determine the cumulative density function using techniques similar to Riemann sums, modified to make the best use of the computer's computational resources. Consider the problem of finding roots to an equation computationally. Often, we begin by considering an interval where we know a root must exist. For continuous functions, the boundaries of such an interval must have opposite signs. The bisection method finds the root by repeatedly splitting the interval and taking the half that still has opposite signs. Newton-Raphson and secant methods use the slope at a current point to estimate where the curve should intersect the x-axis, which may sometimes not converge. Brent's algorithm combines bisection and Newton-Raphson. Multidimensional analogs exist to solve for more complicated roots. Consider Carnot engines. Using the heat transferred at the isothermal parts of the cycle and the conserved quantities during adiabatic parts, we may show that the temperatures are proportional to the heat exchanged by the engine. This defines a scale for temperature. Here is the formula for engine efficiency, with modifications for heat pumps, refrigerators, and realistic effects. Consider reversible and irreversible cyclic processes. They either lose heat or do nothing to surroundings. Reversible parts are path-independent and can define entropy. Splitting a cycle into a reversible and irreversible part demonstrates that entropy is greater than or equal to 0. Groups of particles typically have 3n minus 6 degrees of freedom. 3 per particle, subtracting 6 for the position and orientation of the group as a whole. Each holonomic constraint lowers the degrees of freedom of a system by 1. For example, a system with 3 initial degrees of freedom, but 2 holonomic constraints, has only 1 true degree of freedom. We may express the state of a system in a number of independent variables equal to the true degrees using the holonomic constraints. Through some manipulation, we may construct generalized forces upon these new variables and apply them through Lagrange's equations. A tensor is invariant if its components are the same in any Cartesian basis. In other words, transformations do not affect its components. Second-rank invariant tensors are multiples of the Kronecker delta. Third-rank invariant tensors are multiples of the Levi-Civita epsilon. High-rank invariant tensors are formed as linear sums of tensor products of the above. Earlier, we covered how an operation on a vector that gives another vector can be described as a tensor. We may thus calculate tensors for rotations, reflections, inversions, and projections. These tensors have some relevant properties. Recall that measurements are eigenvalues of the operator associated with the observable. When performing such a measurement, the system collapses to the eigenstate associated with the eigenvalue measured. Measuring again would lead to the same result with probability 1. If multiple eigenstates are associated with the eigenvalue, it would collapse to the associated plane in the vector space instead. Observables are compatible if they do not affect each other's remeasurements. This is equivalent to other formulations. A complete set of compatible observables is one where their combined eigenvalues describe a system with no degeneracies. We may associate tangent vectors at a point with directional derivatives with Cartesian derivatives as a basis. These form a tangent space at a point, allowing forming a vector field for all points in space. Derivatives along a curve can be associated with specific elements in the tangent spaces of the points the curve passes through. The dual to these vectors are one-forms. They act on directional derivatives as expected, and can represent integrals of curves instead. Ricci calculus conventions describe balanced placement of indices for simpler equations combined with Einstein summations learned last semester in introductory fields.